And today we're going to be hearing about tensor product approximation-based methods. So take it away, Ors.
Oh, thank you very much for the kind introduction. And I also thank for the invitation. And I really enjoyed listening all the talks in the past days and participating in the discussions. And I learned a lot. It was great to hear the different opinions and perspectives. And I think this is a very interesting and hot field. And I'm looking really forward to it. Okay, so I will talk about these tensor product approximation-based methods for electronic structure calculations. And this is something a little bit an extension of what Libor has talked about DMRG and MPS. And today we exchanged some slides and the talks, and I realized that there was an overlap between my talk and Libor's talk. So about the applications, I made changes just a couple of hours ago. So I will show a couple of other applications motivated also from the physics community, but using quantum chemistry approaches. And that's basically what is in my mind. So the work that I'm going to present is, of course, in collaborations with a lot of people and many groups and colleagues from physics, from quantum information theory, from condensed matter physics, from quantum chemistry, and then also from colleagues from the mathematics community. And so this is basically an incomplete list, and I apologize if someone is not listed, but we have a lot of work that has been done in the past. So maybe a couple of words to spend on these open problems, because that's actually also the subtitle of the session. And we already had these discussions in the past days, but maybe just to refresh. So from application point of view, we had already great talks yesterday. And so I would like to just focus on open questions or motivations from the point of view of computational aspect. So basically, this open D and S shell electron systems, transition metals, heavy elements, like these molecular magnets and extended periodic systems are something that are each important, because we want to do something that to capture efficiently the static, the strong correlations, and then the dynamic, the so-called weak correlations. So basically, we are looking for the strongly correlated multi-reference systems, reaction paths, transition states, avoided crossings, and of course, the various embedding methods. Usually, it's an important task to do some automatic selection of the active space, the choice of basis. Then also for heavy elements, we need efficient treatment of relativistic effects. Of course, the efficient treatment of excited states. And then when we come to dynamics and time evolution, then questions like coupling to environment, dissipative systems. It's often the case that we start evolution from an initial state and then reaching some final state, but in between, there is some kind of barrier that we have to get through. So this is also an important question, that how to get around this. Also including finite temperature or beyond Born-Oppenheimer approximation. And in general speaking, we are interested also from physics and chemistry, like correlation structures, like clusterizations, chemical bonding, multipartite entanglements, and all these things are something that can be measured. So in tensor product factorization, I will focus on the mathematically exact loop-free networks, basically. It's connection to quantum information theory, but just the basic important aspects. Then a few words about DMRG TCC, which is just a method to capture dynamic correlations. And so I changed the set of applications that I will show, and then I just want to show something that some applications, which is a kind of bridge, like bringing closer the physics and chemistry community, in the sense using this quantum chemistry ab initio method, accessing some problems that motivated by lattice models. And this is done through this so-called Fermi mode transformations that we are working on currently a lot. So I will show something on this two-dimensional Hubbard-like systems, also for long-time evolution. I think a finite temperature I will skip now because of lack of time. But I will show something like some DMRG simulation on the new quantum state of matter predicted by Eugene Wigner some 80 years ago. Then maybe something about this topologically protected correlated end spins in carbon nanotubes. Then I briefly mention polarization issues and some of these multipartite entanglements. So the key idea is that we have a Hamiltonian which has the one particle interactions and then the two particle interactions. So this is in second quantized form. And this, of course, this is possible to extend for higher order terms as well. Now, DMRG provides state-of-the-art results in many fields just based on this Hamiltonian. And in lattice models in condensed matter physics, we usually have some lattices where we have some localized orbitals sitting on the lattices. So we have in this case real space DMRG. In quantum chemistry, these creation and annihilation operated to C plus C are related to some electron creation or annihilation on some orbitals. That would be quantum chemistry. This can be, of course, spin dependent, so that is unrestricted Hartree-Fock. Now we can use also spinors, so that then we can have the 4-component relativistic DMRG, or we also have something like extensions to include proton and neutron orbitals. In this case, we have the JDMRG, so just to do the nuclear structure theory calculations, or go to momentum space, and then we have the KDMRG. Or, for example, use Hermite polynomials, and then you can do some calculations for confined potentials and so on. And of course, there is still a big room and a lot of variants that you can introduce. And then the same machinery, the same method can be used for many things and for many fields. Okay, so the major aim is to obtain the desired eigenstate of the Hamiltonian, and of course, measurable quantities calculated from the given eigenstate. Now, symmetries, we can include abelian and non-abelian quantum numbers like SU2, SU3, SU4, and so on, like double groups in the relativistic version. We can have also complex integrals, quaternion symmetries, and so on. And we will see this so-called number of block states, so that when we do this representation of these tensors in terms of matrix products then, or tensor products, then this is usually that how large, what is the rank of these matrices. Nowadays, it's about between 1,000 and 50,000, of course, depending on the different applications. And in chemistry, for the ab initio, we have usually some 70 electrons and 70 orbitals. And we have access to the 1 and 2 body reduced density matrices. That is very important. So as Libor already mentioned, that if we have some finite system, so it's we call this discrete tensor product space, so that we have some one particle basis like alpha 1, alpha d for d orbitals. We just simply take the tensor product of these bases, and there's a coefficient u, this tensor, and this is basically the coefficient tensor that you want to find by solving the Hamiltonian or the given eigenvalue problem. There's also an extra index gamma. This is just refers the given eigenstates that we are looking for. So this is a tensor which has, in the present case, 8 legs, and alpha are called physical legs because for each of these alpha represents a given physical state. So this is just the basis. And then in quantum chemistry, for example, you can have a zero state and a state occupied with downspin or upspin or doubly occupied. And of course, this blows up the dimension of this exponentially. This is what we call this course of dimensionality. So the system size is pretty much limited, and that's basically exact diagonalization. So we are seeking for some data sparse representation of the wave function. And just a little bit more general way than the MPS, as we heard from talk of Libor, then the idea is that we can factorize any higher order tensor. So that means that a tensor with a lot of legs is a product of tensors with lower orders. So in the present case, in the top, we see that there are 5 outer legs, alpha 1, alpha 2, alpha 4, alpha 5, and alpha 6. So this is a tensor with 5 legs, and that is factorized as a product of tensors. Each box represents a tensor. And the alphas are the so-called physical legs, and then the virtual indices, which are just in the middle, those are actually the legs of the tensors. So U1 is basically a tensor with 2 legs, so this is just a matrix, while U2 has 3 indices, but this U2 has a rank as an order 3 tensor, but it doesn't have any physical leg, so this is just a virtual tensor. While U3, for example, this is a physical leg and then has 2 virtual legs and so on. And U7 is, for example, there are 2 physical legs and 1 virtual leg. So there's a large freedom that how we want to factorize a given tensor. And this is a very big, interesting question, that how to find the best or quasi-optimal representation of a tensor, how to factorize it as a product of lower order tensors. Now, each line in this graph means contractions, so a summation on some common index of the tensor. And this tensor on the above has a loop, while the tensor below, this is a tree which doesn't have any loop, and this can be separated into 2 networks if we cut anywhere. So this is the one that is used in DMRG and then in 3 tensor network states, where we can use single value decompositions to optimize the matrices and tensors. So the simplest representation is just the matrix product state of DMRG, or in the mathematics community called as tensor train, which is nothing else but a product of matrices, so that the U tensor is just factorized as a product of matrices. And if we just write this out, then we basically obtain nothing else but a different representation of the original matrix or tensor if we don't have any truncation. It's also important to mention that we can introduce anywhere a G and a G minus 1 as inverse tensor, so that basically there's a redundancy in the representation that's also called gauge freedom, and there's some aspects about fixing the gauges. Now, the key idea is that we want to control the ranks, the MIs, so that we don't want to keep the original dimensions, and that's actually the heart of all these approximations. And this is what was done by Steve White in '92, introducing DMRG, which of course later on turned out that has the same similarity as the matrix product states introduced already earlier before by the AKIT model. And Ifre Vidal and a group of Franca-Strata, they also introduced these. And then later on in 2009, the mathematics community also came to these tensor factorizations, and they called this tensor train. And in quantum chemistry, around the early 2000s, and there were a couple of groups following Steve White's work. And then let's try to use this for quantum chemistry. And then since then, this has evolved to I think it's to a big field now. And then I think it's an intensively developing work. Okay, so extension of the DMRG for higher dimension networks in physics already happened in the past. And of course, the simplest was to take a 2D system and go through the system like a snake. And this was done by Steve White and Rainer Noack. But in this case, the short-range interactions become long-range. And of course, this generates a lot of entanglements that you need very large ranks to represent your system. A natural extension was introduced by Franca-Strata to go to PERS, this projected entangled pair states, where it's a more generalization of the MPS, so that now we have tensors which has 4 legs, but the scaling, it has d to the 8 or even worse scaling, so it's much higher than DMRG. Now, as a compromise, we can go for a higher tensor network, and that would be, let's say, the 3 tensor network state, where again there are no loops, and for each physical index shown by a vertical line, there is assigned a tensor, and the order of the tensor is again arbitrary, so that we write the psi now as a 2-dimensional plane from these A tensors. And the big advantage of this representation is that the maximum distance between 2 sites now scales logarithmically with d, with the distance for whenever the coordination number is larger than 2. So the coordination number is equal to, this is the MPS, the DMRG, the matrix product state. And then whenever we have a larger z, then we have one of these tensor network states, ansatz. And we have to keep it on the other hand mind that the scaling of one iteration step to optimize such matrix based on single value decomposition, that scales to d to the z plus 1. So in DMRG, this is d to the cube, while in the tree, for example, is d to the 4 or d to the 5. So there's an extra cost for a single optimization step. Now, just like as the psi, the wave function, we can also factorize the Hamiltonian, and that's actually a matrix product operator or tensor. Here is a 3-tensor network operator. And of course, again, you can do whatever factorizations you want, but usually you factorize it in the same way as the wave function. And again, you make contractions also vertically. So DMRG is a polynomial scaling, which is nice. Here is m cubed d cubed, where m is again the number of block states. And in the talk, sometimes I use capital M because this is from the old DMRG community, and sometimes I use capital D because this is from the MPS community. The small d, this is like the dimensions, so the number of orbitals. So it's m cubed d cubed plus m squared d to the 4th. So it's a polynomial scaling. It's a cost-like, so it's a multi-reference method, which is excellent for strongly correlated electron systems. It's variational. It's very important that if we include increase m, then systematically we get better and better results, and we converge to the exact solution, but always from above. Now it's size consistent for appropriate choice of active space. And DMRG can be combined with standard methods like the couple cluster, so leading to DMRG TCC or an FPT2, and also use combined with SCF, so we can do DMRG SCF or DMRG-based class SCF to optimize the basis. Now, usually there are 3 main important questions that how to choose the optimal ranks, how to choose the active space, and then optimal network structure, how to choose the optimal basis. And these are connected basically to quantum information theory. So if you have a system where, let's say, we put the molecular orbitals and then we just next to each other, and then we just separate them into the left and right part, we can calculate the reduced density matrix just by simply taking the reduced density matrix, taking the density matrix of the whole system and trace out the left or the right part. So this is this trace A, then we get rho B. If it takes rho log rho B, then basically we end up with the so-called von Neumann entropy. And this is just a kind of measure that how mixed the given state, so how it's correlated with the other part. Now, if we systematically increase the size of this block, then we can basically obtain the so-called block entropy profile. And in condensed matter physics, this was used a lot. And for certain systems, for example, for critical system where integrable system, there are also analytic solutions how these profiles look like. And also there are extra features depending on the boundary conditions and on many other things, so that we can also provide the position of the soft modes and all these things, the excitations, just by studying the ground state wave function and the entropy. So we don't have to calculate all the excited states. And there has been a lot of work. And the idea would be just to carry over all these things to quantum chemistry. Now, in quantum chemistry, it's more complicated because we don't have a homogeneous system, but we have these molecular orbitals. And of course, the orbitals are different. So let's separate just a single orbital. Then this would be just the site entropy or the single orbital entropy, if we calculate the entropy of this. And this tells you that how much this orbital is correlated with the rest of the system. While we can also get P and Q. In this case, this is the so-called mutual information, which tells you that how P and Q are correlated with each other as they are embedded in the whole system. Now, keep it in mind that the single orbital entropy and the block entropy, these are really the entanglements. So this is really the quantum nature, because these are calculated for a pure state. While the mutual information, when we calculated the SPQ, where we put together this joint system, this is no longer in pure state. So that the mutual information includes the classical and quantum correlations. So it's important to call this as total correlations, or always name it as classical and quantum. And there's a recent work from a group of Christian Schilling from München, where they also introduced some kind of further definitions using the super selection rules, that how to separate correlations into classical and quantum just based on this mutual information. And there are some follow-up works on that. Okay, so what is important is that the orbital entropy, this here I just show you the lithium fluoride at the equilibrium distance, so that at 305, and then when we stretch it, for example. And on the panel above, you can see that how the single orbital entropy looks like at the equilibrium distance, and then how it looks, for example, in the stretch geometry. And of course, you can see that different orbitals get different important weights. And that's exactly the idea, that those orbitals which have the largest entropy, they provide the largest contribution to the correlation energy. So when we select the active space, we really have to, we calculate such orbital entropies with some low-cost DMRG with small m or d values. And from these robust profiles, we can already identify which orbitals are the most important, and these we can keep in the active space, and systematically, of course, we can update it. And there was some automatic selection of active spaces by Stein and Reyer, and recently Golub, Antalik, Weiss, and Brabetz coupled these schemes with machine learning, so they are trying to teach some algorithms that what would be the best orbital sets for the different elements coupled to different environments. Okay, so the other thing is that if we now take a look at the mutual information, then we get some two-dimensional connected graphs, as you can see below, so that there is also on the left panel something for the equilibrium distance, and then for the right for the stretch geometry. And so the idea would be that we would like to have tensor networks which reflects this correlation and entanglement graphs. So the simplest would be the 3TNS, where let's say that we just have a coordination number z equals 3. But this has a problem that we cannot update the ranks dynamically, because when it's separated to two blocks plus the site, then the next block that we want to update, it will never have more Schmidt values than the original one. So basically, it's not possible to do a dynamic rank update. But if we include virtual tensors, which we can see in B, then it's an intermediate step between 3 and MPS. And here, dynamic updates is possible, plus it has a more favorable scaling. And there is, again, some example for the lithium fluoride or for the N2 dimer, where there are some reference calculations for the given ranks with DMRG, with U1, and even with SU2 symmetry, and then with the blue and then the red curves, and then the corresponding T3NS, which is always 1 or 2 orders of magnitude lower in energy than compared to the DMRG, just for the same bond dimension. So that looks nice, but we have to keep it in mind that the scaling of a single step is worse than the DMRG. So this is the DMRG, as we have seen, is k to the 4d squared, k to the cube d cube, where here k is now the number of orbitals, and d is again the bond dimension or the number of block states. while in the tree, we have d to the 4th, and then also d to the cube for the memory, and then for the disk. So it's important that there's going to be a crossover between DMRG and the tree if we want to really get and push tree in a way to access the problems which are basically not possible by DMRG. Or basically it is possible, but maybe we get a better scaling and faster results. But we have to work on it hard, because so far the system sizes that has been reached, there was some gain with tree, but if we consider the CPU without massive parallelizations, then DMRG used to be the winner. But it's also important to mention that T3NS provides more options for parallelization, so that even it is even more scalable in terms of supercomputers. Okay, now everything that I have talked about is now for fixed basis, but we know that everything is basis dependent. So what if we just make a change in the fermionic mode so that we have a unitary operation, and then therefore we just have a new set of operators? And the idea is that we can have such a global unitary applied on the wave function psi, and so that we have our MPS matrices like A1, A2, A3, AN, and then we apply this global unitary on it. Now, if you want to calculate this global unitary, this is very costly. So the idea is, let's do this also iteratively, just as we do the DMRG. So take two component tensors, we do an SVD, and then we optimize it by keeping the Schmidt values, which has the largest weight. And that's basically how we optimize the DMRG, as this was described in detail by Libor. Now, let's split up this GU also for action of gates which are applied only on two tensors. And let's calculate the Schmidt spectrum before application of the GU and after the application of GU, and by some cost function determine that whether we keep the rotated basis or not. And for this option, we used to use the so-called half-range entropy. And then if the rotation has lower entropy, then we keep it, because the main idea is that we would like to reduce the entanglement in the system so that we can lower the bond dimensions. So graphically, where we have just a joint tensor, in DMRG we split it up into two parts, and then we truncate it. Now, instead of that, we take these two, we multiply it with some GU, and then once we have this rotated tensor, then we do the SVD, truncate, and we just check this cost function, and we have if we have a lower range entropy, then we keep it, and we update the interactions, the T's and V's, so that basically we obtain a new set of integrals. And this we do for all steps in the DMRG, so that basically we optimize for all A matrices based on these rotations, and then we update our T's and V's systematically. So let's take an example. Let's take a beryllium atom, which at the moment, let's take its 2s and 3p electrons, so that we have 4 orbitals per beryllium, and we took a beryllium ring of 6 atoms, and therefore we have a chain of 24 sites. And if you start from the Hardy-Fock orbitals and you run DMRG, then to reach a very accurate results, and we had to have some 8,000 block states, so that the ranks sometimes went up to 8,000 that we had to keep track of. While if we do this mode optimization, that after the first iteration, we already have these light blues where the maximum is only 6,000. And after the 10th iterations, we obtain the same results with the maximum ranks about 300, which is this light blue curve in the bottom. Now on the right panel, the same is shown, that how we can monitor the convergence, so that if you take the Hardy-Fock orbital, this is this dashed blue line. If we switch on the orbital optimization, then you can see that for the same bond dimension, so that keeping, let's say, 256 states, then we can gain an order of magnitude or 2 orders of magnitude improvements in energy. Now, starting from Foster-Boy's localized orbitals, which are shown by the red dashed lines, we can also do the optimizations, and then we got again some improvement. So this is pretty general, and this can be done anytime. And what happens is that originally, if you take a look at the mutual information, then it was pretty much non-diagonally dominated, and after all this change of basis, then it became pretty much diagonally dominated. So there's a cost function that one can measure, taking the mutual information, weighted with the distance, and sum it up. And that's actually something that we also monitor and make some judgments about accepting or dropping the rotations through the course of the algorithm. Okay, so this was from the chemistry to the But what can we do about in physics? And then basically something that I mentioned that bringing closer physics and chemistry community is, let's say that we have a two-dimensional spinless Hubbard model with nearest neighbor interactions. And then again, this we can study with the snake-like approach with DMRG. Also, we have a periodic condition in both directions so that we have basically a torus at the end. And this is a nightmare for DMRG. But if we do the optimization on the matrix product state manifold and on the Grassmann manifold, so that we also allow rotations on the orbitals, then this Hamilton can become long range so that we end up again with this quantum chemistry like Hamiltonian. And that's actually the connection. So we can use the same quantum chemistry DMRG codes. And here, just an example for an 8x8 lattice with the different colors, I show that what was the reference energy obtained in real space in the original basis with different bond dimensions. And then this red and the black one shows you that what is the energy using optimized modes. And the black one is basically the one where we used 256 states. And we reached the same accuracy that was reached with 4,000 states in the real space basis. So also it is possible that we can calculate the 1 and 2 particle reduced density matrices. Since we keep track of the rotations, we can always back rotate our operators to the original basis so that we can also study quantities like correlation functions, charges in waves, and so on. So we get a much better finite size scaling than in the original problem. We got a big reduction in the bond dimensions, so it's much faster. And of course, after back rotations, we can really analyze what are the modes, how they look like. And so to see that what happens, it's basically we can also see that monitor the profile of the block entropy. And it is clear that the block entropy from the original basis, which is this blue, drops systematically. And in the optimized modes, basically the block entropy profile was reduced by a factor of almost 10. And this, keep it in mind that this is on a logarithmic scale. And of course, this can be done for as a function of interaction, so that for real space basis, the block entropy, for example, diverges for u equals 0 or v equals 0, while in this optimized mode, that would be just the momentum space representation, and we get it for a 0 entropy with a bond dimension 1, so it's just a product state. And also for the large V limit, which can be considered as a strongly correlated states, it's again, we just have a single determinant, because in this case, it is just a charge density wave, so that basically with the bond dimension 1, we basically have the solution, and we don't need large-scale DMRG calculations in the real space. And extensions for the 2D is also on the way. And I just selected this 6x6 Hubbard model at u equal 4 because there are published data in the literature. So like this full CI QMC, AF QMC, PDMAT, and DMAT, shown by the dashed lines, these different methods. Of course, many of these are not variational, so we have to keep it in mind, this fact as well. And then we can see that the DMRG optimized basis with this red curve, as you can see, as a function of bond dimension. Okay, now the same idea can be used also in time evolution, so that if you perturb a system at t equal 0, then we generate some quasi-particles and they collide with each other, and then they just generate entanglement. And then as we do the time evolution, they generate more and more entanglement. So at some point, the entanglement will increase in the system, that the bond dimension will increase systematically, and then we will be blocked by simulation because we won't fit into the computer, so this determines the simulation time. But if we, again, combine this with this adaptive mode optimization, then we can expand this time frame by several factors. And that's exactly what has been achieved. So that there are different methods to do time evolutions, like the TDBD, the Krylov space, or the one which is so-called this time-dependent variational principle. And this is very good for systems with long-range interactions. And again, in the TDBP, shown in the right panel, this is again application of pairwise gates. So going back and forth in the DMRG or on the system, this corresponds to a single time step. And if we do this, we can do the time evolution. And just as just to mention that we can also do imaginary time evolution using the same procedure. In this case, it would be like a ground state search, as here is shown for the F2 molecule. And TDBP is also has been applied also by Bayard and Ryer also. But let's see that just a quick example that something that we are working on also in quantum chemistry is that, let's say that we take a spinless fermion system and then we just prepare it in a charge density wave and let it evolve. And therefore, we can measure the imbalance between the occupation number of the even and odd sites. And then with blue, I show what would be the imbalance with the exact calculation. And the different color shows you the different results using different bond dimension. And for R equal A, this is actually the bond dimension. Now it's labeled with R. it already starts to deviate from the exact solution around time 0.7. While if you take the same article 8, but with the adaptive mode optimization, it starts to deviate from the exact only around 2.5 or 2.7. So from 0.7, we went up to 2.7. And that's exactly the one thing that what we are doing. And what happens is that if you monitor the one particle reduced density matrix, for example, if you do the exact solution, then we can monitor that how it looks like. And of course, it gets more and more terms which are diagonal off-diagonal terms. But if you do the rotated basis, then we always, after rotations, we get again more or less recover this diagonal structure. And that's actually what happens, that we can optimize the modes, which are always optimized for that given time step. So basically, it's good to abandon the fixed basis picture also for higher dimensional problems and also for time evolution. And the same can be used also for temperature. Now, Libor already talked about TCC. The idea is that we have a full space, which we separate into two spaces, the T-CAS and T-external. And the CAS and external space, we can calculate the cluster operators, that would be Tx and Tcas, and therefore we can just factorize the CC wave function according to this. And the idea is that the CAS space is solved by DMRG. From the DMRG, we get the matrix product state, and from this we get the CI coefficients from which we can build up the cluster amplitudes for a given truncation, so that we did the CC single doubles. And Libor has shown already that if you do this TCC in this chromium dimer benchmark, then with a very small active space, you can recover 99% of the correlation energy, and then which is much better than even the CCSDTQ. Okay, but this is nice, but also we want to understand a little bit more about this, and we work together with the mathematician colleagues that what are the errors which comes into the TCC. And so basically, it is important that it can be treated as a nonlinear Galerkin scheme. And two important results that it provides for a fixed CAS solution. So it's important that first we fix the CAS space, and once the CAS space is fixed, then it provides a unique approximate solution, and also it provides the minimal error from the exact solution for a fixed basis sets. And all these assumptions are based on the fact that we assume that the Fock operator has a so-called CAS X gap. So we put operators into the orbitals to the CAS space, and if you take the lambda eigenvalues of the Fock operators, there's going to be a gap between the last lambda k belonging to the CAS and between the first belonging to the X. And if we do this, then we can show that DMRG TCC has a quadratic error bond. And I don't want to get into the details, but basically in the middle you can see some formula where we identify the different terms, and there is some error terms coming from the DMRG, just approximating the CI. There is something that due to the truncation of the CC, then also some methodological error by keeping the amplitudes of the CC part fixed where we do the DMRG, and then when the CAS is kept fixed while we do the CC. But for a given CAS, working through all these things, it can be shown that finally we obtain a quadratic error bond. But finding the optimal CAS, basically there is no compact results yet from point of view of mathematics, and it's a pretty hard problem. So what we did is that we did some numeric studies that simply forming a CAS at the beginning where there is no orbitals in the CAS space, but everything is in the external. And if you do TCCD, then of course this is nothing else but CCSD. So what we have seen, what we can see here, an example for the equilibrium geometry of the N2 dimer, then reference energies from the CCSD, CCSDT, and CCSDTQ with these different dashed lines. And then K is a variable which just takes that how many orbitals are placed into the CAS space. So that basically we just sweep through with DMRG. It turns out that we can also use different truncation schemes, different approximations for the DMRG, and the profiles looks pretty much robust and same. And of course, you can see that it's not a smooth function, but there is a lot of irregularities. So usually if you find something, a lowest error with low bond dimension DMRG calculations, this is what we found for accurate large-scale DMRG as well. So even if there is no nice results from point of view of mathematics, in practice, what you can do, you can sweep through with cheap DMRG calculations with low bond dimensions, the CAS space, and then look for this error minimum, and that might be also, this is what we use also to fix the cost space in these calculations. And then once it is found, and then we do the large-scale DMRG calculations together with the CC corrections. Okay, now it is possible to extend all these to... Yes?
Oh, 5 more minutes.
Sorry?
5 more minutes before we...
Yeah, so it is possible also to do this for relativistic regimes. That would be the 4CTCC, and then also for complex integrals, just to quaternion symmetries and things like that. And this is something that we are working on. Okay, now let me just show you one thing that brings closer also to physics and chemistry community. That, let's say we take a nanotube. In this nanotube, there are these end spins which are topologically protected, and there are so-called in-gap states for U equals 0. And then when we switch on the interactions, then we have the ground state has basically a spin which is related to the number of the edge spins. And of course, to do real space DMRG would be a nightmare, but we can again do the change of basis or find a suitable basis so that we express the one particle Hamiltonian. And from this, we do the diagonalization, we find the one particle basis states, and then we express our the Coulomb integrals based on this basis. We use this so-called Ono potential. And if you do all these things, then you can show, for example, that the couplings between the two end spins can be are dependent on the length of the nanotube. So you can make from an antiferromagnetic to a ferromagnetic transitions, also changing the dielectric constants. You can tune this, so it's important, might be important for applications in quantum information technology and so on. So what I'm just trying to say that again, we do this physics motivated approach, but then we end up with the quantum chemistry Hamiltonian. And some other work is that, for example, if you take a nanotube, which is called the system nanotube, and then you take another nanotube, which is called the probe nanotube. Now there is so-called scanning charge techniques now that in a Weizmann Institute, a group of Ilan Shalani, they can put 1, 2, 3, 4 finite number of electrons into such nanotubes put into confined potentials, and they can basically see that if someone puts a finite number of electrons into the system, then what is the charge density distribution. And just keep it in mind that in the nanotubes you have two spin states, so up and down, and you can also have two chiralities. So you have an SU2 cross SU2, which is an SU4 symmetry. So if you have electrons and then you just put it into the particle box states, then you can put 1, 2, 3, 4 particles into the same state, and then you will have two peaks when you have 5, 6, 7, 8. If there is no interaction, but if there is a strong interactions between the electrons, then when you put two electrons into the system, you immediately see that they repel each other, so that you will see as many peaks in the scanning techniques as many electrons you have, and this is what they have exactly what they have measured. And that would be actually where a system where you have very low density, very strong Coulomb interactions, and that's actually would be the Wigner crystal, which Eugene has predicted some 80 years ago. And let's do this with DMRG. Again, with real space basis, it is impossible. But what we did, we just took some basis harmonic oscillator states centered at the classical positions of the atoms. And then, of course, with some techniques, we just built up some complete states and run DMRG on that. That we again ended up with the quantum chemistry Hamiltonian. And what you can see here with RS, this is just the scaled interaction strength. And that's a DMRG result with this great scale, so that if you put one electron, then you see basically as a function of the interactions, it's only one peak. If you have two electrons at some point, you see 2 peaks and 3 peaks and so on. So that's actually DMRG simulations. And then the green stars shows you that where the experiment measurements are, to what points the experiment measurements corresponds to. So basically the DMRG predicted the position of the electrons exactly the same place where the experiments have shown. So there's a very good agreement. Again, this is something which is a nice thing because we are using the quantum chemistry methods, but now we are studying something from physics motivated models. And also the same you can do also, for example, something like this boron vacancies as a qubit centers, where we combine the DFT with Kohn-Sham orbitals, and we put DMRG on the top of it, and so that we can also target excited states, and then we just reproduce the full photoluminescence spectrum by DMRG, which agrees pretty well with the experiments, as you can see with this little brown and then with the blue curves. Okay, so all these things are very important. And just one final remark is that these basis optimizations, you do it with cheap calculations, so that with low bond dimension DMRG, so that, for example, all this can be done in GPU. So that's some work that we did in 2014, where you can show that with DMRG you can reach the theoretical maximums of a GPU cards. Now this is integrated now with multi-GPU cards. So basically all these basis optimizations and section of active spaces and things like that, finding an optimal basis can be done in this framework. And then, as Libor already mentioned, this is also doable and possible on the CPU level, and then do large-scale calculations with large bond dimensions on supercomputers. And I will skip these last two slides. And so I will just conclude the talk that with DMRG TCCD, very large active spaces can be treated. These different entropy measures are useful tools to optimize networks and, of course, to gain information about the system. This local mode transformation is very important, and it has an important connection also to what Steve White has presented yesterday about his approach. So there must be some kind of connection. It would be good to study this in the future. We can do long time evolution just by doing adaptive mode transformation to expand the time evolution frame. And of course, in general speaking, the message is that cross-fertilization of development in physics and chemistry can lead to very efficient novel algorithms. And I thank you very much for your attention.
Wonderful. Thank you very much for the great talk, Ors. So we've got a number of questions on Slack. The first one is from Matthias de Groot. He asks, do you use the same bond dimension in the trunk and the leaves of the T3NS?
Say it again, I'm sorry?
He asks, do you use the same bond dimension in the trunk and the leaves of the T3NS?
Yeah, the bond dimension is the 3, and then the TTNS, and then the DMRG, we use the same bond dimension. This is what was the idea, to show that what is the gain if you use the same bond dimension, that whether the tree can do better. But of course it can also take the same amount of time, because as I said, that the optimization step that scales with d to the z plus 1.
So Urs, my question would mostly be, could you gain something from tailoring and having a different bond dimension at different levels?
It is possible also, yes, definitely. So also because of these different, so what is important is that we have these different kind of correlations, so these range separated correlations or something like that, so that of course for the different parts you can do some fine tuning, so that there might be that you can separate your system into based on this. What I wanted to say is that basically what you can do is that you can have a better or worse representations of the different parts in your system related to the different correlations. For example, if you have an impurity model, then around the impurity you can use some different techniques to get the correlations over there. And then of course, maybe with the environment you need just a more robust version. Is this an answer to your question?
Yes, sure. Thank you.
Wonderful. We've got another question from Steve White. The question is, can you make an ansatz, potentially involving some simple calculations, to get the optimal single particle basis to reduce the entanglement in a DMRG?
I mean, this is what we would like to have. So that's exactly some goal. With this mode optimization so far, at least based on the figures that I have shown, so this is basically based on some entropy criteria. So that this is basically just reducing the entanglement based on the Rayleigh entropy. So if we have a condition that we enforce, then I think with this mode optimization we can find a suitable one particle basis which fulfills that condition. The question is that whether our conditions was the best one to achieve a given goal. So that maybe we can change our conditions, and this is also something that we are working on, or there are some ideas around, but maybe, as I said, this might be connected to Steve's work, so that basically I think it would be good to maybe to combine things together, and but this cost function that of course determines also that how the optimization flows.
What, can I follow up a little bit? So you use the Rayleigh entropy, and is that you compared with the von Neumann, the different entropies deal with the tails differently. You might think that the Rayleigh entropy might be better.
It's a half Rayleigh entropy. it has a kind of amplifying property. So it's sometimes where the small values get smaller, large gets larger, so that it's basically something that it's not a uniform. So it's basically has such a feature, and this is why we chose it. And but of course, you can choose against something else. And then we also play with the mutual information as a cost function, but this seemed to be so far the most robust one. We also did extension of this for bosonic systems, but then of course it got tricky, and we need some modification, other cost functions, so it's not straightforward to do it. Also, the MPO, the matrix product operator structure also gets more and more dense. So this is also important to mention. But again, with these modern technologies, with parallelizations, it's not a problem if something gets more and more dense because you use more and more CPUs. So that the question is that if you can reduce the bond dimension, because this basically determines the memory. So if you can reduce this, but we have more and more components, which we parallelize more and more, then basically we again gain something. Of course, we use more CPUs, but we fit into the memory.
Great.
Wonderful. Actually, Ors, if I could ask one really quick question.
Mm-hmm.
From the perspective of the quantum computing crowd in here, what would you say are the biggest impacts that, apart from understanding, getting a better understanding of what the limitations of classical methods are, what the biggest impacts of the techniques you've developed might be on the quantum computing community?
I mean, that was a very interesting talk from Maya Studmeyer 2 weeks ago, where he just showed his MPS simulation of these random circuits, and then about what fidelity he could achieve. And of course, he has shown that up to some point, of course, it looks nice, but then of course there is the kind of barrier which he hits, and of course this is the quantum supermassive, which is by the way is really there. So it was very nice, and so that I think maybe providing wave function as initializations for quantum computers, I think this is something for these hybrid algorithms. That's something might be, I think, useful. So, or combine, or maybe some of these, like as what Steve mentioned yesterday, he also showed his idea as a two-gate operations, and this is what we have also in this mode of transformation, so that we always apply it only on two components, and then you do this step by step. So maybe this can be combined or carried over, and I think something in this direction would be possible, but I don't want to say anything stupid, but no, I mean, so it would be great to discuss about these things.
Wonderful. Thank you very much for the great talk, Ors.
Thank you.
Can I ask a quick question?
Oh, we're running low on time. It's very quick.
Can you just briefly comment on the tensor networks with loops? Any advantages, disadvantages?
We have a proposal which we just turned in with the mathematics colleagues from TUM, where we introduced adaptive network tensor networks, including loops, so that we are changing the tree, some points to loops, so that in quantum chemistry, there are a lot of these organic molecules, or you have these loops, and actually, which I skip now in my talk, but we just have something. With the loops, there is a problem, because it's mathematically not exact, but there are these injectivity theorems and others where you can get around this, but you have a much worse scaling. But in quantum chemistry, this will be very useful, because you don't have thousands of loops like in PEPs, but you just need a few loops, and having these few loops will most probably get you some benefits compared to the simple TNS or T3NS, and that's something that we try to work on in the next years.
Thank you.
Wonderful. Thank you very much.